Every single second, across the globe, thousands of people flick their thumbs left or right on a screen, attempting to form a human connection. Behind those simple gestures is one of the most volatile distributed computing environments in existence. To operate Tinder, the system processes 75 million daily active users and 2 billion swipes, registering every action in under 200 milliseconds. Engineering this with a standard monolithic SQL database exposes immediate scalability limits. Running standard mathematical queries to find nearby users requires full table scans that quickly time out. Simultaneously, synchronously writing 2 billion swipes to disk instantly exhausts server connection pools. The engineering challenge is contradictory. The system must serve broad read queries for geographic matches, while concurrently processing highly consistent, targeted write queries for swipes. Solving this requires 3 distinct capabilities: proximity querying operating in constant time, non-blocking swipe ingestion, and matchmaking logic that guarantees 2 people are matched exactly once. Achieving this means abandoning standard relational database principles and adopting a highly segregated distributed systems architecture. The first computational hurdle is the read path. When you open the app, it needs to instantly generate a feed of potential matches near your physical location. Calculating the exact physical distance between you and 75 million other active users using a standard SQL radius formula is computationally impossible to do on the fly for every single feed refresh. Instead of raw coordinates, the architecture utilizes geospatial sharding. The system maps the Earth onto a discrete, flat grid. The world is divided into geometric shards down to cells roughly 1 kilometer wide. The system simply identifies the grid cells that intersect your search circle. Users are stored in in-memory data stores, like Redis or Elasticsearch, indexed entirely by their cell ID. As you travel, your phone periodically reports its location. An asynchronous worker checks if your coordinates cross a cell boundary. Only if you enter a new cell does the system update your index assignment. This transforms a heavy, math-intensive spatial distance calculation into a lightweight, constant-time key-value lookup. The database simply retrieves all user IDs listed in your surrounding cells. Geospatial sharding makes proximity discovery computationally sustainable, allowing the system to scale without the limitations of the standard database read path. Once the system retrieves nearby candidates, it faces a second bottleneck. It must ensure you are never shown a profile you have already swiped on. A highly active user might have thousands of historical swipes. Checking a new batch of 50 candidate profiles against a massive relational database table to see if they exist in that user's history creates severe network latency. The solution is a Bloom filter, designed for incredibly fast membership checks. A candidate profile ID runs through multiple hash functions, mapping to a compact bit array. If even one bit is 0, the system knows instantly the profile is new, bypassing disk lookups. Bloom filters have a specific trade-off. They can yield false positives, but they guarantee 0 false negatives. You will never see a duplicate. To maintain speed, candidate feeds are pre-computed and stored in a Redis cache and filtered through this probabilistic layer right before they are sent to the client. Accepting a tiny margin of probabilistic error is a necessary trade-off. It is the only way to achieve sub-second feed generation while filtering against millions of historical records. With the read path optimized for discovery, we have to look at the highly volatile, high-throughput write path, the swiping mechanism itself. Globally, the servers absorb over 20,000 unpredictable asynchronous swipe actions every single second, creating an intense, volatile burst of write traffic. If the mobile app waits for a synchronous database write confirmation before letting you swipe again, the UI will freeze. A 50-millisecond network delay would ruin the continuous psychological flow of the application. The architecture completely decouples the swipe action using an asynchronous, event-driven design. The API gateway drops the swipe event into a high-throughput message queue like Kafka and instantly returns a 202 accepted status to your phone. You keep swiping with 0 lag. Behind the scenes, the event is processed safely. A fleet of parallel consumer workers pull these swipe events from the queue at a sustainable pace. The labor is divided. A cache worker updates the Bloom filters in memory so that person won't appear in your feed again. Concurrently, a database worker persists the permanent swipe record into a write-optimized wide-column store like Cassandra. An asynchronous queue acts as a shock absorber, protecting core databases from write spikes while maintaining the illusion of instantaneous speed. While the feed and caching layers tolerate eventual consistency, the final step, match generation, requires absolute, strict logical consistency. The system must account for a specific distributed systems race condition, user A and user B swiping right on each other at the exact same millisecond. Concurrent workers checking simultaneously see empty states. Mutual likes are recorded, but zero matches. To fix this, workers use a canonical pairing key for a pessimistic row-level lock. Transaction A locks and writes. Transaction B waits, reads A swipe, and safely creates the match. Pessimistic locking creates a tiny bottleneck, but it is a non-negotiable safeguard. It guarantees exact once-match creation, protecting the core value proposition of the entire platform. When we zoom out, we see a distributed architecture built on strict isolation. Location updates route immediately to the geo-index. Feed generation pulls directly from the Bloom-filtered Redis cache, and volatile user swipes drop straight into the Kafka event streams. This performance relies on extreme segregation, completely isolating read-heavy geographic discovery from write-heavy transactional matching logic. Because these foundations are decoupled, data science teams can inject heavy machine learning recommendation models just before the caching layer. They can rank candidates and predict compatibility without ever impacting the user's swiping latency. Operating a global dating platform requires massive computational complexity, but by mastering the limits of distributed systems, geospatial sharding, and event-driven architecture, engineers compress that complexity into an experience that feels effortlessly instantaneous.